So last time we started the last chapter, desalination. We went through the basics of desalination, and also we saw the first type of desalination, which was multi-effect desalination or distillation. Now the second method of thermal desalination is this one, multi-stage flash desalination, right? So it is very similar to the previous one here, but the main difference here, the heat transfer surface was actually a coil over which this seawater is separate, right? So the heat transfer is taking place between this separate seawater and the outer surface of this coil, which is heated. But in this type of desalination system, which is flash desalination, there is no heat transfer coil, but the whole fluid itself as a bulk will evaporate. That is the major difference, right? So the vapor formation which takes place here, it is from the bulk of the fluid, bulk liquid. In the previous case, it was from the hot piping surface. Okay. So here, let's try to understand what is happening. Here is the seawater at around ambient temperature. It is now coldest. Now it enters into this third stage, then second, and then this is the first stage. Why it is first stage? Because here the heat is supplied at the highest temperature from whatever is the heating source, boiler or if it is a cogeneration plant, or it's an exhaust of any power plant, exhaust gases of any power plant. Right, so here is the highest temperature steam is supplied, which will transfer its heat to this seawater, which was already preheated in previous three stages. So here it was coldest, here it will be colder, and here it will be cold. And now it is heated, preheated here. So in these 1, 2, 3 stages, it has been preheated. Now here it is heated at the highest temperature. Now it enters into the first stage. Now first stage is just a flash. Here it will flash. Flash means the water vapor will be separated here because it is at highest temperature. So vapor will rise up, and here it will come in contact with the cold surface and it will condense. So only pure water vapor will evaporate. The rest is the brine, which is left at the bottom, and that will flow to the next stage, right? Here the water is separated just by flashing water vapor, because here pressure is maintained low. So in this, as we move in this direction from first stage to second and then to third, pressure is dropping. Okay, so here is pressure in those vessels is reducing. So as we move in this direction from left to right, in each stage, pressure is gradually dropped, which means boiling point is also reducing in this direction. Okay, so whatever water has been evaporated, it will be condensed when it comes in contact with this cold fluid. So this condensate is a pure water which will be separated here. That is the fresh water. So this brine, which is left here, now it will move into the next stage where pressure is further lower. So here, because of the reduced pressure, boiling point is reduced, so some more water vapor will evaporate here. Now this water vapor will come in contact again with this colder seawater coil, and it will be condensed here. So the same will be repeated in the next stage, the third stage. So whatever brine left here, now it will enter into a third stage where pressure is lowest. So now some more water will evaporate at lowest temperature, and it will come in contact with the coldest seawater, right? So whatever water vapor is evaporated, it will be condensate. So all of these condensates will be collected, and this is the fresh water. And here is the concentrated brine, which is separated. Okay, so this process can be repeated even up to 15 to 20 stages. Here only as an example, only 3 stages are shown, but it may continue up to 15 to 20 stages. And in each stage, pressure is reducing. Okay, so hopefully the overall working principle of this system is also clear. It is very much similar to the previous one, but here the water in bulk is being evaporated, right? So its efficiency compared to the previous system is low because here water vapor is not properly evaporated by coming in contact with the heat transfer surface. Because in the previous system, we see in the previous case, here we were using a spray mechanism where water is converted into small sprays, and that comes in contact with this heating surface. So here we get much better evaporation of water vapor from that seawater, right? So the overall efficiency, thermal efficiency is concerned, then MED is definitely better than MSF, the multi-stage, right? Because here in MED, we require less energy, less Q in compared to MSF, right? Because of better heat transfer. Okay. So, yeah. Because in this system, we are using bulk flash, right? Here, there is no heat transfer surface, so here we are relying on bulk flashing, where seawater flashes suddenly into vapor. So here we need a large temperature difference, and some energy is wasted during this flashing, right? So this MED compared to MSF, that transfers heat more effectively with less energy. And in case of MED, the previous one, it can operate at low temperature because of better efficiency, heat transfer efficiency. But in case of flash systems, MSF, the required temperature is a little higher, about 90 to 110 degrees Celsius. Right. And also, there is more scaling and more corrosion, and here we need better materials. All right. Okay. So hopefully, so you can read it through by yourself. I have explained the overall working principle. All right. But still in compared with this, so there are some more figures which you can see to better understand its working principle. So it is the same steam entering into the main heat exchanger, where this seawater is heated to a very high temperature. So maybe I can write some typical temperatures. For example, steam is entering in the range of 110 to 120 degrees Celsius. All right, and it will heat this And here this seawater is entering around 90 degrees Celsius because it has been preheated in the previous stages. So here we can say it will leave around 100 degrees Celsius, right? And whatever is the vacuum pressure which is maintained here. Here for to create vacuum pressure, we can use a vacuum pump, or there is another system which is called ejector steam that is based on convergent divergent nozzle. So that's if you are interested, you can further see how it operates. And the purpose of this ejector type of steam system is to produce vacuum pressures. Okay, so now this brine, which is entering at 100 degrees Celsius, pure water will evaporate or flash. We use the term flashing here, right? And here the water, the temperature of the brine will reduce to about, for example, 95 degrees Celsius and then up to 85 and so on. So in this direction, the temperature of this brine is dropping, but the pressure is also dropping. So that's why in each stage, some vapor is generated, and that is condensed air separately, right? Finally, maybe brine is leaving around 55 degrees Celsius, round about here. Sea water or saline water has entered at around 25 ambient temperature, 30 degrees Celsius, and in each stage its temperature was increasing, and maybe it may reach up to 90 degrees Celsius. So here is the main energy supply, and that goes back to whatever is the energy source, power plant or whatever. Same phenomena is again shown in a different way, and another schematic, right? Maybe it is more, if this is more easy for understanding. So here again, you see the same heat source. Here is the seawater, which is heated. So it's flashed, comes in contact with this colder coil, condenses. So here we have a separate collecting mechanism. Okay. And this will be transferred to the next one. And here this brine is transferred to the next one. And here you see a kind of a throttling valve where pressure is reduced. Right. So again, steam is evaporated, or pure water vapor is evaporated, condensed, evaporated, condensed, and so on. All right, so here is the seawater entering. This is the last brine whose temperature is still higher. So this can preheat this seawater, right? If this brine temperature is still higher than seawater, so here we have uh, another heat exchanger, which is also called regenerator. So here, this one particular stage is shown separately, where you can further see what is happening in each stage clearly. So here is a throttling mechanism where pressure is dropped, evaporation takes place from this brine, right? Here, evaporated water comes in contact with this cooling surface, so it is condensed here, and this condensate is our pure water. Okay. Okay, let's move to the next system. Next type of thermal desalination system, that is called vapor compression desalination. All right. Just like in a refrigeration system, we have vapor compression refrigeration system, but here this is vapor compression desalination system. Here we are using a compressor, and see here in that vessel there is seawater. So above the seawater there will be vapor, pure water vapor. Now this water vapor is taken. For example, here pressure is kept very low so that this vapor is evaporated at some low temperature. So for example, some typical value, if I say if here the pressure is 0.3 to around 0.5 bars, so water will be evaporating at around 70 to 80 degrees Celsius. Now this water vapor is compressed in a compressor. So when you compress a gas, so its temperature will increase. So for example, here temperature rises to around 110 to 120 degrees Celsius. Now this high temperature vapor is brought into that uh, channel, or which is surrounding this seawater vessel. So what will happen, this high temperature vapor will transfer its heat to this vessel in which we have this seawater. So the energy to heat this seawater is actually coming from this compressor, because compressor has increased the temperature of that of that vapor, pure water vapor. So this pure water vapor will transfer its heat to this seawater, and during this process, it will condense. And this condensed water, pure water or fresh water, can be collected separately. So in this system, seawater is evaporated using heat from this compressed vapor, that is compressed vapor at high temperature. So in this system, we need a mechanical compressor, or there is another type of compressor, steam jet ejector, which you can study by yourself. There is another system, because you already covered how a nozzle operates, so you can understand there is another type of compressor which is called steam jet ejector. Okay, so this can be used to compress the vapor. So this compressed vapor has a high temperature and is reused to heat that seawater in that vessel. And during this process, the vapor condenses. Okay, so this type of system is suitable for small scale installation, for small scale installations. For example, in ships or in remote areas. So it's a very simple setup. Low maintenance is required, but such systems are not used for very large applications. Okay, then it becomes not economically feasible. So for very large applications, normally MED or MSF systems, thermal desalination systems, are used, especially if there is a cogeneration plant, if there is a waste heat available in power plant. So that is the most common technology used in all over Gulf countries, especially this MSF, because MED is although more efficient, but it's more costly. Its maintenance is much bigger because you are using spray nozzles and heat exchanger piping, etc. But MSF is just it's just flashing of the steam is used here in MSF. So both are used for large scale installations, these two ones. For small scale installations, this is also very efficient vapor compression desalination system. Okay, so hopefully this is clear. So just read it through by yourself. Here you see another schematic to further explain the same thing. We can use the same vapor compression system in this way. So here, let's see what is happening here. Here is again this saline water. It is first preheated, right? Uh, Preheated with this compressed air. So let's see, go through step by step. Now it is this preheated seawater is finally here. We are using a spray mechanism. Spray mechanism will result in better heat transfer efficiency. Now this is separate over this heating coil in which there is a compressed vapor coming from the compressor at high temperature. So this seawater is separate over this coil, heated coil. And here we have some low pressure maintained in that vessel. A vacuum is created. So from this seawater, pure water vapor will evaporate, and that is flowing towards the compressor. Okay. So this is another way to utilize the same system. And in the compressor, temperature is increased. So here is high temperature vapor is entering into that coil. So in that coil, it will transfer its heat and it will get condensed. Okay, so still this temperature is higher than seawater, so it can be used to preheat that seawater. So here it's another heat exchanger, okay, which is used as a preheater of this seawater or brackish water. Okay. So this is another way to use the vapor compression system. Okay. So advantages and disadvantages are mentioned here. Okay, it's clear. It is compact, definitely and portable. Minimum pre-treatment is required. Less complex feed water preparation. Cost effective because the capital costs are not that big. High quality output. They can process low quality feed water. Then RO, the next system which we will see. The system overall is expensive equipment, requires large, costly steam compressors. And of course, you need to give electrical energy to derive that compressor. And of course, there is scaling, corrosion risks, evaporator components exposed to feed water. Okay. Okay, let's go to the next system. So far, the previous three systems, MED, MSF, and vapor compression, all are uh, considered or known as thermal desalination system because we were heating the seawater to evaporate fresh water or pure water. And the major source of energy is in the form of thermal energy. That's why those are known as thermal desalination methods. The next method, which is not a thermal based method, that is called reverse osmosis. That is very the most commonly used around the world is actually this reverse osmosis system for desalination purpose. So in this RO system, there is a membrane is used here, for example, in this figure. This is reverse osmosis film or membrane. So this is a membrane-based separation process. And here, pressurized seawater is forced to flow through this membrane, right? Through this permeable membrane, right? Permeable means these membranes have very, very small holes, uh, maybe in the range of 0.0001 micrometer of holes are there in these membranes. These membranes are made up of some special polymeric materials, and this hole size is so small that only pure water will pass through. And all the solid particles or ions or which are or the waste particles, bacteria, those will be separated because their sizes are higher than this one. Okay. But here the issue is that we have to supply a large pressure, right? So pressurize water has to be supplied. So for pressurization, we have to supply energy. Okay, to raise the pressure of this incoming saline water, so that this pressure difference here and here across this RO membrane, this should be higher than the pressure with which this water will start to flow here. Because if there is no, if it is not pressurized on this side, so what will happen here? The concentration of pure water is low. Here, pure water is low. On the other side, the concentration of pure water is high. So if there is no pressure on this side, so this high concentration pure water will start to flow in this direction. So this pressure is called natural osmotic pressure. So that's why we have to supply a high pressure on this side so that these pure water should not start to flow in this direction. Because here the concentration of pure water is low. Here the concentration of pure water is high. So if there is no pressure on this side, on the other side, then this naturally the pure water will start to flow in this direction. So here in the system must be pressurized. There must be a mechanism to give a high pressure all the time. Okay, so this pressure is normally in the range of, for example, 55 to 70 bar pressure is normally applied on this side. Okay. So here on this side, about 55 to 70 bar of pressure is normally applied so that the pure water can penetrate through this membrane, and here again the brine is separated, right? And special polymeric materials are used here to construct such membranes, right? Okay. So this, I saw that name polyamide is is one type of synthetic polymers which are made to achieve this task. Okay. So this is the working principle of this system, which is called RO system. Um, so and this is the pressure required on this side if it is seawater. Especially for seawater, we need high pressure. For brackish water, which is less salty, we may need lower pressure. 15 to 25 bar is also enough for brackish water. Okay. Okay, so the output is collected here, which is fresh water. All right. Uh, Same thing is shown here in this system. Here is the saline water. Initially, you can pre-treat to separate bigger solid particles. Here is a pressurization system, some kind of pump, for which again you need only pure electrical energy. There is no thermal energy interaction. It's pure electrical or any other type of energy which can raise the pressure of the fluid. Okay, so here is the membrane where the pure water is separated. There may be a need of post-treatment to further clean it, and the fresh water is collected here. Okay, so that is just a very brief intro about the reverse osmosis system. So, okay, so this is the material of that membrane. Okay, the rest simply you can go through by yourself. Okay. Another system, another membrane desalination method. Here again, it's not a thermal. That is called electrodialysis. So here, electrical energy is used, or an electric field is used to remove uh, ions, ionic compounds. Ionic compounds are elements present in that seawater. So this can be used for small applications, but this is not used for seawater, but normally for brackish water, this type of system, because this can only remove ions, right? It cannot remove the suspended solids, right? Or other non-ionic compounds. Okay. So now let's see how it operates. So it uses an electric field. For example, here you supply a DC current. It has a positive pole and it has a negative pole. Here is the seawater, which is made to flow through these partitions, right? And here you see cation selective membrane, this one and this one. And there are alternate cation and anion selective membrane, right? So when the seawater is entering, so now what is cation selective membrane? Those are actually negatively charged. These are negatively charged membrane, for example, made up of some, for example, SO3 negative group, right? What they will do, they will allow only the positive ions to go through, and they will block the negative ion. They will block negative ions to pass through these two cations. And the opposite is happening here in the anion selective membrane. Anion selective membrane, they have positive charges. For example, Nr4 group, they will allow only negative ions to pass through, and they will block positive ions. Okay. Okay, so the purpose of these two cations and anions is only to block the opposite charges. And these electrodes, these poles here, negative, and these positive poles, they are the ones which create that push or force, which will pull the ions present in that seawater. They only allow the correct ions to pass through when DC field is applied. Okay, so this negative pole, they will attract positive ions. So here you see in that seawater, whatever positive ions are there, those will be attracted towards this negative pole. And this membrane, cation membrane, will also allow only positive ions to pass through, and they will block the negative ions. So negative ions will be flowing towards the other side. All right. So here we have anions. This one is anion, right? Show it properly. So here, these positive ions, those are attracted towards this negative pole. And here is a cation selective membrane, which will block negative ion and will allow the positive ion to pass through. So the purpose of the membrane is just to block the opposite charges, but the force to attract those charges is given by these electrodes, positive or negative. So now we can see here clearly what is happening. Here is the seawater, which is distributed in these columns. Here in the middle ones, you can see the positive ions will be flowing in this direction, negative ions will be flowing in this direction. Okay. For example, here in this one, positive ion is going here, negative ion is going here, and these positive or negative are collected here in the middle one, and also in the last one. The last column is collecting positive. Here on the other side, the negative column is collected. These two columns, this one and this one, here pure water is collected, fresh water. Right? Positive was moving towards the negative pole, negative was moving to the positive pole. So here in the middle, you have those collection of positive and negative ions, which is collected separately, not only from the middle, but also from the last two. Because seawater is made to flow from here, here, everywhere, but here this seawater is collecting on those ions. Okay, so those are separately collected, which is the concentrated brine. Okay, so hopefully the basic working principle is clear. Here, There is a limitation because this system can remove only ions, ionic charges, like Na plus or chlorine minus, such ions which are present in those water, right? So this is used, this type of system is best suited for brackish water, right? With low salt, not for seawater, because it cannot remove the solid particles, neutral particles. Okay, so but still, this is also used to desalinate normal water. Okay, so hopefully this is clear. So just to read through the working principle. All right, and the step-by-step method, which I have already explained. So that is it. Let's go to the next method, a renewable energy method, which is called solar desalination method. Solar desalination method, here it could be both thermal or non-thermal, means where we can use electrical, we can produce electrical energy from a solar system, or we can convert this solar radiation to thermal energy. So here we can use both types, thermally based desalination system or electrical or force based desalination system. So in this figure, we see thermal solar desalination. So here is the seawater, right, which is supplied from a seawater tank. So what we can, and at the top of that vessel, there is a glass cover, right? So what this glass will do, it will allow the solar radiation to pass through, right? It will not absorb solar radiation, or very negligible amount will be absorbed. Some small amount will be reflected back, but major will be transmitted. This transmitted solar radiation will be absorbed here in this seawater. And at the bottom of that seawater vessel, it is actually this basin that is also painted black, so that maximum solar radiation is absorbed here at the bottom surface and also in this seawater. So what we can assume, what we can expect, of course, with the absorption of the solar radiation, the temperature of this water will increase. And with the increase in temperature, pure water will evaporate. So here you see this evaporation is shown. As it evaporates, so it comes in contact with this cold glass. Glass is cold because glass is not absorbing solar radiation. Glass is only allowing this solar radiation to pass through. So its temperature will be lower. Here temperature will be lower than the temperature in the basin where we have that seawater. So when this evaporated water will come in contact with this cold glass, so it will condense here. So these are the condensed particles are shown. So those condensed vapors, those will be flowing along the length or along the surface of that tilted glass, and that can be collected at in a separate channel towards the end. Like here in this configuration, you see here, this is single sloped glass is used. Here the double sloped glass is used. Double sloped glass. There are many different variations of solar thermal desalination systems. Two such systems are shown here. This is single sloped. This is double sloped. So here is the water vapor, which is evaporated, and here it is condensed. And this condensate is collected separately, shown here on both ends. This is the distilled or clean water, right? The whatever left is brine, which can be collected separately. So here, the source of energy is thermal, which is actually solar radiation, which is converted into thermal energy. when it is absorbed here at the bottom of that basin, or when it is absorbed by this salt water. Compared to clean water, this salted water has high absorption of solar energy, right? So this solar desalination, it is using solar energy either in thermal form or in electrical form. So here we saw only the thermal desalination types of solar desalination, right? So this seawater is here placed in a very shallow basin. It should not be too thick, because if it is too thick, then solar radiation will not be absorbed properly. So the thickness of that this seawater is very important. It should not be too thick. It should not be too thin, right? So solar radiation is actually heating this water, which will cause this evaporation. Okay. This basin, I already told you, it is normally black. Black in color to increase the efficiency of uh, absorption of solar energy. Okay. So this is solar desalination, but in other systems, we can use this solar energy with the help of those photovoltaic panels to create direct electrical energy. Okay. This electrical energy can be used to derive a pump, which can be used to pressurize the water for RO system. So this is the second way to use solar energy. All right. Solar energy. So here in these two systems, we are using directly solar energy directly, either in the form of thermal or in the form of electrical. These are the direct use of solar energy in the form of heat or in the form of electrical energy. But there is an indirect use. We can use this solar energy to produce steam first, and then we can use that steam in MED or MSF system, multi effect desalination, or multi flash system, right? So that is also possible, MSF system or MED system. So here is the brief explanation of solar desalination. All right. Here is a summary of this solar desalination system. We can use solar still, direct use of solar energy. Solar desalination is also called solar still. Right, so this is what we saw in the previous slide, direct use of solar thermal energy to evaporate and condense. The second is direct use of solar energy to produce electrical energy, this one. And we can use solar-based RO systems where solar PV cell is used to produce electrical energy, and that can be used in RO. And this one is indirect, this one or this one. Okay, humidification. This is another system which we have not covered. Okay, that is another type of desalination system, humidification and dehumidification. That is not very common, but if you are interested, read it by yourself. But we can use solar energy here in solar MED or solar MSF system. That is the indirect use of solar energy. Okay, these are clear, of course, advantages, freely available, limitations, because this process of solar desalination is very slow and we get very low output in a given time, right? And also the solar has the limitation because it is not constant or all the time available. That depends upon the availability of solar radiation. That's why it is intermittent in nature, and also high capital cost for our large scale solar based MED or large scale solar RO systems. Here you see a solar desalination system, which is used for MSF, right? Multi-stage flash system. It is the same system which we covered, but here the major source of energy is coming from solar thermal collectors. It could be parabolic trough, which is used to produce high temperature fluid. Here is the storage, and this high temperature fluid is used here, which is serving as a boiler to produce steam here. Okay. Uh, and this is the seawater, which is heated up in that boiler, and then it goes into the flash system, which we already covered. Okay. So here we are using solar energy indirectly for a multi-stage flash system, or it can also be used in multi-effect desalination system, MED system. Okay, so this was all the different types of desalination systems which we have covered. The next part is the thermodynamic modeling of single effect evaporation, right? So here this part is the detailed thermodynamic modeling. Okay, so I will see if I can make a separate video on it, but I think that will be difficult now already. Semester is already over, but this part I'm leaving for the time being. So I will see in coming weeks if I can make a video about it. So here it is the detailed thermodynamic modeling. So let's keep it here. Still have 2 more days after vacations, so we can finish it there. So we'll see if we can complete this part also. So for the time being, this still till slide 21. This part is covered in this chapter. The thermodynamic modeling part is still left. Okay, there are few students. Okay, you can mark your attendance, and that is all for today.